successful, a lot of algorithms have to work on the backside, and a lot of sensors have also have to work together. For example, it make use of a lot of sensors like radar, lidar, GPS, IMU that will perceive the surroundings or environment around it. Then it will plan a path from the source to destination, and then it will maneuver autonomously through a dynamic environment where there will be a lot of objects. And so there are a lot of hardwares involved and a lot of algorithm processing modules involved for the autonomous driving or selfless cars to work successfully. So these hardwares and these algorithm modules require a framework, which require a framework so that they can work together as a single entity. There will be a lot of sensors, will be there, a lot of ECUs will maybe there, then a lot of algorithms for perception, planning, decisions will be there. But they have ultimately they have to work together and work together as a single robot or a single entity. That's where the robotic operating system come into action. It is a mature and flexible middleware, and it has got a lot of modern libraries, tools that can access and analyze the sensor data. Then it is possible to process them and provides control information back to the vehicle actuators, say steering angle, brake, accelerator, actuators, etc. So this robotic operating system, it is the backbone or a software middleware that will help in the communication of the various modules between each other. So ultimately, robotic operating system, it is a publish subscribe system. Like it will, as in the figure shown over here, we can say you can say a lot of nodes are present. You can say if there is a lidar and the lidar module is there, you can say assign a particular node for the lidar module. The module can be think of as a node. Or you can, for the radar, there will be a radar module or radar algorithm processing module. It can be a node, another node. And for camera, there will be another node. And these nodes will be work together and collect objects and get the object information of the surrounding. And these object informations will be published as a message or as a topic. So there will be a lot of nodes will be there, and they will be publishing their messages. And these messages can be subscribed by another nodes, say planning decision modules that will be used with this object information that they are getting from the lidar, radar, camera modules. And these informations will be processed by another node, such as a planning decision module or maneuvering module, and they will generate another informations like the planned path or the control signals back to the vehicle. So these signals will again be published as the messages. So all these entities in the ROS environment, they are called a node, and all these nodes can work in parallel, and they can generate the messages, and they can communicate with each other. So this is how the ROS robotic operating system or the ROS environment work at the base level. A part of this topic, there can be service messages also. Service is like topics will be the messages that will be published every time at the particular intervals. And in some cases, there is no need of topics that or messages that is publishing at the particular every time. So one node, in that case, we can assign services also. Like in certain situations, the node will ask for a particular service from another node. Then this will request or initiate that service request to this node. Then this node will provide the service back to this node. So the service messages is also provided by the robotic operating system. So the main advantage or the feature of the robotic operating system is this publish subscribe feature. That is all the nodes can communicate with each other by means of the messages or topics or services. And another important thing is robotic operating system is a open source. And anyone can download the ROS software and install to their Ubuntu machine, and follow the tutorials to create the package and create their own nodes or programming modules, and can generate messages and start working. And some other features why this ROS became popular are it can be used in a lot of platforms, like robotic system can be working in the Ubuntu machine. You can use Ubuntu, or it can be used with the Arduino platform, or it can be used with other software such as MATLAB, and a lot of then a lot of visualization tools, libraries tools, everything will be available for the ROS. A lot of features are there, and they are cross compatible to many hardwares, and many languages will be supported, and many versions of the ROS will also can communicate. And the application developed in different versions of the ROS or different operating system can communicate with each other and work together. So all these features made ROS an important entity in the autonomous vehicle R&D purposes. Apart of autonomous vehicle area, it is also mainly used in the robotics, and it has got many other applications. ROS has got many other applications in the field of medicines, medical areas, or industrial areas, manufacturing areas, where the applications of the robot is very necessary. So ROS is primarily made for robotics robotics industries, and we can have a small information regarding what are the other applications of the robotic operating system in industry. Where all these robots are used, and where all these robotic operating ROS software will be coming into use. A brief introduction regarding it only. So coming back to our autonomous car subject. So this is an architecture provider for architecture provided for the self-driving cars. So the main hardwares are the acquisition sensor, like it is a LiDAR, then radar, the IMU sensor. These sensors, that is the perception sensors, will perceive the environment by taking the data, sensor data, like LiDAR will provide the point cloud informations of the surrounding. Then radar will give you the velocity information of the object together with the position information of objects. Then IMU will give you the position of the of the ego worker with respect to a global reference. So all these are all the acquisition sensors. They will collect the data of the about the informations of the surrounding, and it will be acquired by perception module. So, but the main perception module will also have a lot of algorithm stack is provided for the environment recognition, then ego work localization, that we have to localize the position of the ego worker with respect to a global reference. Then environment recognition also is necessary with the help of the sensor data, so that it is possible to classify the obstacles, detect the obstacles, find its shapes, and classification is possible. And we have to calculate the behavior of the objects and predict its next state, so that accordingly the self-driving car can predict its path and maneuver suitably. Then the information from this perception module will be given to the planning and decision module. They in turn plan a path from one point to another by avoiding the obstacles, and then plan their mission and maneuver from one source to destination accordingly. Then for that, the decision module provide the control signal, that is lateral, longitudinal control signals to the control modules, and it will in turn provide these informations to the steering wheel, and accelerator, brake, throttle as throttle informations to the throttle brake. And by using these signals, the vehicle in turn will start driving. So this is in high level, that is in a brief manner, this is what is the architecture provided inside the autonomous self-driving cars. So here we can see that a lot of sensors are involved, a lot of hardwares are involved, then a lot of algorithm modules, perception module, plan decision module, and with their corresponding algorithm stacks are involved for the self-driving cars. And the communication means we can each vehicle or our self-driving car can take the information about the other vehicles in their surroundings or from the infrastructure by vehicle-to-vehicle communication. Such a module is also like vehicle-to-vehicle communication is another developing or almost developed domain in the industry now that will aid in the self-driving or autonomous vehicles for their maneuvering. So it is processing the information from V2X is also vehicle to other communication. Vehicle-to-vehicle communication information is also necessary for proper decision and planning the path. So all these modules, algorithm modules, sensors, everything needs a common framework or software as the middleware, and it is provided by Robotic RAS layer or robotic operating system software. And these are some of the features that is provided for autonomous applications. So why we have chosen the robotic operating system or RAS software for the autonomous vehicle. Because they contains a lot of libraries and tools. Some of them are listed over here. So first of them is like sensor analysis framework. Like all these LiDAR, radar, IMU, GPS, all these sensors will have their own sensor drivers, and RAS will provide the tools for data for analyzing the data from these sensors and visualizing them. And RAS will have another 3D visualization package called RVIS tool, RVIS, for visualizing the 3D data or processed data or radar data, anything. And here we can see a video over here that will be played at the end of this slide. Then another feature is the data logging and replay framework. Like for development of the algorithms in the RAS autonomous software structure, it is necessary to log the data from these sensors and replay it while developing and testing. So the RAS will provide the tools for recording the data from the sensors together with the timestamp and replay it later. And it is also possible for synchronizing the messages from different sensors possible based on the timestamp. And it is possible to replay these data sets later at the same rate at which it is recorded based on the timestamp. So simulation time as well as real-time supports are provided, and tools and libraries are available for this. And another feature is the presence RAS wrappers or RAS bridge code for interfacing. Like this RAS algorithms will be developed might be developed in the different languages. Maybe it will be CPP or Python, or it may be developed in the MATLAB. So the RAS a bridge code or bridge module should be there so that it is possible to establish the communication between algorithms working in the different environment. So RAS wrappers will provide such bridge code. And basically, another feature is it is a middleware framework that will establish the communication between different nodes in the RAS environment. Like maybe it is a LiDAR node, radar node, planning node, or maneuvering establishing node. Maybe whatever be the algorithms, it is possible, it is necessary for these modules to communicate with each other. So such interfaces and communication infrastructure will be established by RAS environment. And it will also provide the debugging and the profiling tools. And next one is the 3D visualization. We can visualize the sensor data as well as the processed data. And the RAS TF library, transformation library, means these sensor data will be providing the data based on the sensor coordinates. We have to transform these coordinates to our vehicle coordinates so that all the data from different sensors will be in common reference. So for that, a transformation library will be provided that will have a lot of packages or functions that will take this, that will make use of the function that will take care of this transformation and all. Here, after processing, like another one is a multiple information overlay. It means a lot of data will be coming from different sensors, and we will be processing it, and there will be processed data. So a lot of informations will be there. We can see it in the visualization tool by overlaying one to another. We don't have to develop a visualization tools from the scratch for visualizing and analyzing it, because already there will be packages available for that. Here we can see a video, small video of the RVS tool, how it is moving. Oh, this is our ego car or self-driving car, and this will shows the point cloud from the environment that is detected by the lidar sensor. We can see this. These are the car parks on the either side of the road. There is we are following another car. Pedestrians are there crossing the road. So this entire visualization is supported by the RVS tool. It is a default. It is provided by the ROS as a default tool. So it is all we have to do is select a sensor, collect the data, and visualize it in the. We can visualize it in the RVS tool. So this is a brief visualization of the tool provided by the ROS. Similarly, we can generate our custom data, and we can visualize them in the visualization tool and all. So these are some of the features provided by ROS for supporting the autonomous application. So thus we can, and one more feature of the ROS is it is based on the ROS master. Like, yes, it is one of the ROS one environment. So we can say that there will be a lot of nodes are there, like it is a talker or it is the publisher. Like one will be publishing as a information, and other will be taking that information, so they can communicate with each other. You can say there is a talker node and as well as a listener node. But before these nodes to communicate with each other, they have to establish register them with the ROS master. We can say it is a master node. So what there will be n number of nodes in the ROS environment. All these nodes have to register themselves with the ROS master at the first. Then only they can communicate with each other. The ROS master will track the communication and track the entity, whether it is active or standby, and all these nodes that is tracking the status of the entities will be taken care of by the ROS master. This is one of the feature of the ROS one, but it has also got one disadvantages. Like if the ROS master got killed, then all these node will be failed. No communications will be failed. So there is a center point of failure over here. So it is one of the disadvantages of the ROS one or initial version of the ROS. Then there some other questions also raised in the industry, which raised the question for next generation of ROS. Because of the some of the challenges faced by the industry. So we'll be going through some of the challenges one by one. Like in the ROS environment, we have as we have defined over the architecture over here. All these architecture have developed over the ROS environment. But there is already a worker domain or another operating system is already present in the worker, ADAS worker, or they are not autonomous workers. In the ordinary workers, already another worker domain is there. The workers are a lot of ECUs will be working in the cars, and these ECUs, you can say one ECU will be there for autonomous emergency braking, one ECU will be there for weather sensing, and a lot of ECUs are already there in the production vehicles where they will be communicating with each other. And for that, already there is an operating system and a standard is present. One of them is AutoSAR. AutoSAR is the existing automotive standard for the embedded systems and ECUs, and it is just like an operating system for the proper communication between ECUs in the vehicle domain. So it is an autonomous AutoSAR operating system is there, and vehicle networking between ECUs are possible based on these standards, and it is mature and fully flourished, and it is presented there in the production cars already. Then we are coming with the ROS operating system with the new autonomous R&D products like perception, planning, decision modules developed upon the ROS, and how these domains will go together. It is entirely different domains. So there should be something so that these two domains, AutoSAR domains or ROS domains, can communicate with each other and go along with each other. The industry have begun to think about the next generation of the ROS. The ROS, robotic operating system, cannot work as a single entity. It has to go to the production. Currently, it is mainly using in the R&D purposes, but how to use it for the production workers, how to go make it to the market, that was the next question. So people have begun to think about another middleware so that it is possible to establish the communication between AutoSAR entities and the entities in the ROS. So that was one challenge faced by the autonomous self-driving vehicle industry. Then another challenge is like there are a lot of sensors involved, like camera, lidar, radar, etc. So camera will be giving a lot of video streams. It consists of a lot high data volume, and data frequency will be less. For lidar also, it will be generating the point cloud information that we have seen earlier in the RVs2. And there also the data volume will be very high, and frequency will also be very high. But there are other sensors, you can say the control command that will be giving to the actuators, brakes and the accelerators. They will be binary structure. For them, the frequency will be very high, but the data volume will be very less. So there are a lot of sensors are there that will be publishing the data with varying volume, frequency, reliability, and latency. So cardboards may need different data flows, and they all need a particular QoS, that is quality of service, security, scalability, and support these varying data types and network requirements. This is not supported by ROS1 as such, because ROS1 have their own limitations, like synchronization issue is there, and quality of service is not given as a separate parameter. Quality of service means it is a parameter where we can control the flow of data. We can assign the parameters about the liveliness, about the lifespan of the data, and all such quality of service parameter can't be assigned in the case of ROS1. But it became necessary to need such advanced features, and there also people began to think about next middleware or next generation of the ROS. And there came the ROS2. That is the next version. Even though it is ROS2, the basic architecture or the basic middleware that is working behind ROS2 is entirely different. Because industry, people have adopted a middleware called data distribution service. This data distribution service middleware is already it is a networking middleware that simplifies the complex network programming, and it was already using in the many other domains such as battleship, spaceships, flights, etc. So people began to, and it is well matured and was using, and well documents are also provided for this DDS, and different OEMs and industries were already using this middleware for their application. So it was better to adopt this middleware to the new next generation ROS rather than developing another middleware for ROS. That's how it is. Next generation of the ROS, that is ROS2, came into existence with the DDS that is bottom. Here you can see like there is a ROS component and ROS 2 is there, and here there is a DDS database. So one other component we have in the slide we have mentioned that the communication between ROS and AutoSAR is necessary. So here you can see there is a AutoSAR environment prevailing over here, and it can generate the message, and it will be passed over to DDS database, and it can be communicated with the ROS environment. So there are also many other entities that can be built upon the DDS middleware, like test simulation entities are there, testing and validation modules will be there, fusion modules, whether it, and some of them will be developed on the CPP application, another will be on the Python application. So all these modules can publish their messages on the data distribution service middle layer and can communicate with each other. So basically, DDS is a machine-to-machine communication standard, and it helps to its performance is very high, interoperable, and support real-time data passing, etc. So it is also here also the feature of the ROS is adopted, like it is basically DDS is basically based on the publish subscribe system. All these entities can pass their data to database, and some other entities can receive it. So that's DDS will also provide many other features like security, reliability, QoS parameters. All these features will be provided by DDS, and it will provide additional advantage to the ROS 2 compared to that of the ROS 1. Here, this some of the benefits of the underlying DDS middleware is listed, like it is reliable, quality of service settings, like history, how long a particular message was there in the ROS environment. Such informations like history and reliability, how trustworthy the data is, and durability. Such information and the parameters can be assigned by the DDS middleware, and it is based on the UDP multicast, and it supports a real-time application. And here masterless discovery, it means that here we have suggested like ROS 1 requires a ROS master through which all the nodes will be initially registering, then only they will be publishing they will start talk to each other. But such ROS master is not required in the case of ROS 2, because here all the nodes are global, and all the nodes can see each other and communicate each other. And they can assign a QoS parameter, quality of service parameter, also to the for the proper data control over the data. So these all benefits are because of the presence of DS at the bottom of the ROS 2. So masterless discovery is another important feature of DDS that will give another advantage to the ROS 2. Then the use of QoS, it allows the RTPS, that real-time publish subscribe communication layer, to provide reliability in a lossy environment. So if the network is not much efficient, then it will give reliable information how trustworthy the data is in that lossy environment. And it will also support the real-time environments where critical processes are under time constraint to complete. So this feature, QoS feature, is not available for the ROS 1 applications. Then security information is also provided by the ROS 2 because of the underlying DDS middleware. Thus the ROS 2 has come into a picture with the help of the DDS middleware. So these are the areas where DDS were already used by the industry, like the battleship, financial system, space, flight, etc. So here we can see an architecture of the robotic operating system 2 that is built on the DDS. Like ROS 2, it is basically provide a ROS 1 like interface, but on the top of the DDS, or data distribution service. And here this is the architecture of the ROS 2 alone. Here you can see that RTA Connex, Prism Tech, OpenSpace, these are the vendors that will provide the DDS software. And above the DDS software, we can see an API that will abstract the DDS for the DDS that is prevailing underneath. And above that, we can have the ROS client library. That is for ROS 2. It is RCL CPP library. This is the library provided by the for the ROS 2 applications, and you can take the features of the from this library for your own application. And here our code will be user will be developing their application code. So they don't have to worry about what is happening in the DDS, and because all these complexities will be already abstracted by the DDS API, they can develop their CPP code or a Python code by taking by making use of the ROS libraries. And this is the architecture for the ROS 2 only. And here you can see the in higher level how this will be using. Here you can see there is a DDS data layer. Beneath it, there is RTPS protocol is there, and beneath it there will be Ethernet, UDP, IP, or TCP, IP protocols for the communication. And this is the DDS middleware. Above that, we can develop the ROS2 application over here, or there will be another applications, AutoSAR application, or you can have another DDS applications. Maybe it is on C, and or DDS application that is C++. These are not ROS applications. These are separate DDS applications, and all these applications developed by different programmers in different environment can communicate with each other. They can be integrated because of the common platform DDS. So this is the high level architecture. How the DDS will help in communications of the various applications developed in the various platforms, whether some applications will be in the DDS or some will be AutoSAR application, and there will be a ROS2 application. So all these applications can come together and work together. So it will provide a lot of flexibility. And here this slide is already covered. What is one of the main difference between ROS 1 and ROS 2? That is the absence of the ROS master. There is no center point of failure is there. And these are some of the earlier releases of the ROS. ROS Kinetic came, then Melodic Morinia, Neo Ninja Mist. These are various releases of the ROS. In the net, if you go to the ROS, www.ros.org, that is the website provided by the ROS. You can see how long when it was released and how long the support will be provided for the ROS 1. Similarly, there are various releases for ROS 2 also. Dash and Daddy, Meta, Electron LSR, and the recent one is Foxy Fits Rosy. And you can take a version release based on the Ubuntu machine and Ubuntu version and based on the application, and you can develop the application. Then here you can see a lot of advantages. Some of the advantages of the ROS 2 over ROS 1. The main advantage comes from DDS middleware. So it has like it will a lot of switching DDS vendors like will be there. And different processors developed by different vendors can communicate with each other. And DDS middleware can provide QoS, quality of service settings, UDP multi-class, standard shared memory, masterless discovery. All these advantages provided by the DDS middleware can be adopted by the ROS 2. So another advantage is non-global nodes matter. So they don't need a ROS master who will track what nodes in what process. So such a ROS master is not there. Any node can work, communicate, and pass messages with each other. And then multiple nodes can be work together. Then nodes in a single process can communicate through shared pointers. Concept of shared pointers is there. So in the ROS 1, if you want to publish one message to another, you have to wrap it in a proper subscribe publishing manner. Then you have to publish it, and another node you have to unwrap the message, then take it. So all this procedure will be there for publishing and subscribing. But in the case of ROS 2, shared pointer concept is there that will reduce the time of communication between them. Then synchronous scheduled execution of nodes is there. Like in the ROS 1, scheduled execution of nodes is not there. All the nodes will initiate and start work together. But here in the ROS 2, we can schedule what nodes have to start working at what time. Then control over callback concurrency callback group. Callback group means in the ROS 1, a lot of nodes will be there and they will be publishing their messages. And it will cause a lot of constraints in the resource or in the bandwidth in the network. But in the ROS 2, you can time what messages should be start publishing at what time, and what subscribers, some of the subscribers can work together while other subscribers will be in the sleep mode, and when they will be start receiving, the one another set can go to their sleep mode. In this manner, the constraints in the network can be reduced. So control over callback concurrency callback groups is also possible. Then not life cycle management, dynamic runtime features, everything, all these features will be provided by the ROS 2. And these are some of the advantages of the ROS 2 over ROS 1, like real-time performance, QoS, security, portability, and it is also production oriented. ROS 1 was mainly oriented for the R&D purpose, but ROS 2 is mainly evolving for the production orientation. Then, so these are some of the advantages of ROS 2 over ROS 1. So one of the main aim is the ROS should go to the production of the production environment. So there comes the concept of micro ROS. That is, it is also ROS 2, but you can say it is a smaller version of the ROS 2. You can say it is a sibling of the ROS 2. Micro ROS is provides the tools and functionalities of the ROS 2 ecosystem, but it will work with the embedded ECUs. It can work with the embedded ECU. ROS 2 libraries and features cannot go to the small embedded ECUs where the power and memory constraint, RAM constraints are there. So there should be a version of ROS that will support all the features of the ROS 2, but in the resource constraint areas. Thus evolved the concept of micro ROS. So micro ROS consists of a layered libraries that can either use the features of the ROS 2, or they can adapt them in accordance with the resource constraint devices. So here you can see the some architecture of the ROS 2 that is already described. Like here we have a processor, and over that we have our Ubuntu or Windows operating system, and about that we have a ROS middleware interface like DDS for the ROS 2, and all the complexities of the DDS2 will be hidden by the abstraction layer, like ROS middleware abstraction layer above it. Then you can have the ROS library, RCL library, whose features we can adopt for the development of our application over here. So this is the architecture of the ROS 2, and you can see a micro ROS architecture over here. So micro ROS is mainly intended for the embedded systems or microcontrollers over here. And this is a recent technology that have just come to the market, and it is need to be explored further, how it can, what are the features and what are the further advantages and usability. So here the microcontroller is here, and above it the operating system is FreeRTO, real-time operating system, that will be working on the ECUs. Then POSIX, portable operating system extension is there. These are some of the operating systems on the ECU microcontrollers. And then above that you can have the US middleware micro XRCE. Micro XRCE is a software solution, and it allows communication in the extremely resource constrained environment. Like XRCE is extremely resource constrained environment with the DDS network. So this micro, it is just like a DDS middleware, but prevailing on the existing on the ECUs. And over there, you can have the ROS 2 middleware interface and CPP API application library, ROS library is there. About that, we can have the application. Then micro XRC is like a client client server model operation is there. Like if there is a applications that is working on the micro rows, and it can communicate with the applications in the rows too, or DDS, or the any other entities in the DDS with the help of the micro rows agent. This will act as a bridge between the entities in the ECUs and that in the rows 2 environment. So these are the new concept in which the rows 2 can be brought to the ECUs or in the embedded systems. That is micro rows. And here you can have the small video about the micro rows. And this video is also, the link for this video is given in the chat box, the last link itself. If the audio is not if it is not audible, please refer to that link. So here we have covered the evolution of the rows. First, in the R&D applications, we have proposed the rows, and for the aim of production, for using in the production workers, we have gone from rows to rows 2. Then for using the rows 2 in the ECUs, we have come to the micro rows. So these are some of the main milestones in the evolution of the rows. So in summary, so here you can see that it is a graph showing the evolution of the autonomous driving, software complexity, how it is increasing. In the 2013, the main automotive industries was around assisted driving, and later the industry have gone for automated driving, and ROS has played an important role in the development of automated driving, but it is in the research work. And from 2020 onwards, in this area, we have to think about how this self-driving workers should go from R&D stage to the production stage. In this case, the ROS has evolved to ROS 2, then coming recently the micro ROS. So ROS has got a large growing user base. A lot of industries and universities are working together, and more packages are developing and coming to the market, where these packages can be used by by many industries for achieving their goal of self-driving cars. Then a consortium of industrial partners are there to establish a joint roadmap for the development of AV worker. Then quality management and safety qualification is also established by and supported by ROS. Then ROS is basically an open source project with most of the packages are under permissive license. That is, you can take the package, modify it, and you can build your applications. And it supports real-time execution, multi-platform support, embedded system support is provided, and better resource handling is there. So these all features make ROS as an important entity for the development of AV worker. So this is here you can see some of the features provided by Robotic System Toolbox. Like it can interact with the real robot. You can use it for the deploying in hardware, or you can log data, process them, visualize the data. You can use, there is a simulators are also provided where you can interact with simulator tools also. So a lot of features are there, and still it is evolving for making autonomous workers a real experience, really successful for the market. So this is a brief section regarding the ROS and its future in AV work. So in this ROS tutorials, it is given in detail how we can build a ROS applications, build it using the Catkin tools, and develop the applications with the help of a lot of libraries and all. And details about the ROS 2 is also provided. So this is a brief section. Thank you. Any questions from?
Yes. Actually, there are some questions in the chat box. Can I ask?
Okay. I will.
Yeah. So the first question is the perception module available in AutoWare, or do we have to program it?
Autoware means is the perception module available in AutoWare, or do we have to program it? AutoWare means the AutoWare package where the perception will be dataset will be taken with the programming modules. Is it mentioning about that?
Ashik, are you there? Ashik MS?
Anywhere, a lot of industries, a lot of ROS packages are already available for the perception. We can take the data set from this data set, and we can test using these algorithms provided by the ROS packages, or you can develop our own modules and test it. For the lidar algorithms, cameras, a lot of ROS packages and the programs are all provided. Use it, test it, or if you want, we can modify it and create our own algorithms also. Anything is possible.
Okay. So next question is, do the autonomous vehicles that are in production employ neural networks or ROS? If both are used, which one is more effective?
Yes, it depends upon neural network is a recent architecture. We cannot program the algorithms in such a way that it will work in all the entities, like in all the scenarios. There's a lot of scenarios will be coming while we'll be driving on the road. So it is really difficult to program algorithms for all of these scenarios. So it is recently neural network and artificial intelligence have come to assist, where it is possible to train the neural networks and drive it. So drive in the self-driving car. So in but the in the neural network also have got their own limitations, and it is not 100% achieved their it has not achieved their goal 100%. Like a lot of neural network have got a lot of hardware requirement, and it is really difficult to train for all these scenarios. Training is also another issue. So yes, both of them have their own advantages, and both of them have to evolve a lot to come to achieve their goal of autonomous vehicle in market. Neural network is also evolving. ROS, robotic operating system, is also evolving, and we can say that in the artificial intelligence, different types of programming is there. You can say you can simply plug in all the sensor data and create a big neural network, train it, and give the signal to the control signal to the worker. This is one approach, but in that case, the training will be tremendous, and currently such a trained neural network is not in the market or in the industry. The another way is you can take the perception module, and some of the modules will be working in the rows, and these algorithms will be providing some of the information, and these informations will be used as the validation data for the neural network. Validation data for the output from the neural network. Like neural network will be generating one data, and the rows will be generating processed data from the algorithm, and these two data can be compared and validated and provide a better information. This is another method. This is also in progress. So we can
Okay.
which is more effective. Both of them is have their own advantages and disadvantages, and industry also making use both of them to come to a common solution.
Okay. Next question is, can we develop autonomous vehicle with ROS alone, or both ROS and AutoWare is needed?
Uh, was a rose alone, and both are also not aware. Actually, I'm a little ignorant about the auto-wear concept. Can someone tell me about auto-wear? Is it a GitHub like a concept where all the algorithms will be available? Okay, AutoWare is the open source for the autonomous driving.
Maybe he
Okay,
the
AutoWare
one.
is a AI. Okay, it is AutoWare is a AI application that will support the AI solution. I hope it is AI based industry for self-driving worker.
Okay. So next questions. Could you give some examples of microcontrollers that can support micro rows?
Mm, yes, micro rose is just came to the market recently, and I have got this from in these details about and the link is provided over here at the last slide. MicroRose, eProsima, and freeRTOS.org, MicroRose on freeRTOS.html. It is a recently evolved software, and from this link, it is possible to get information what are the microcontrollers they are supporting.
Maybe if you can share the link in the chat box, that would be.
Okay. This Rose 2 is a recent version. It has come to the market by 2-3 years back. And Rose 1 is already there in industries. Someone has asked whether it is better to go for Rose 1 or Rose 2. Like Rose 1 has got, it is more stable, we can say. Like it is already in the industry for last 9-10 years, and it has got a lot of packages, libraries, tools, and it can be really used for our for developing application. It is more mature, but rosto I don't think it is much mature and stable. Like many of the libraries we have to develop, we have to while we are developing the code, we find that some of the libraries are not present. We have to then we have to go to the rose one and find that library and find it. We have to develop our code correspondingly. So if you are not going to the market or not going to the production, it is better. Or if you are using your application for R&D purposes only, then it is better go to the rose one. And if you are going to the production oriented and you are thinking to integrate your rose application with any other applications like the DDS applications will be there, data distribution service, like it is a middleware and a lot of applications can be there. And if you want to communicate or integrate your application with such entities and you need a common platform, then it is better to go for the ROS 2. But for yes, and for market and you are thinking about the security and reliability and the QoS of the data, etc., and then you can go to ROS 2. But for the R&D applications, and we have to develop just to develop the applications and as a on the mother as a part of the a curriculum or as a for the purpose of research and development, then ROS 1 is better.
Okay, some more questions are there. Can we take up 2 more questions?
Yes, yes. Which simulators we can use to create scenarios in ROS 1 and ROS 2? For ROS 1, simulator like Carla is there. And for ROS 2 also, Carla simulator you can take. Sometimes you may need a ROS bridge. Like if the Kala simulator is supporting only ROS 1 environment, then ROS 2 bridges are there from which it is possible to generate the ROS 2 messages from the simulator. Mainly, we have used the Carla simulator for creating the scenarios. Then, will map providers add features to help self-driving cars detect obstacles, or will it be responsibility of supercomputers embedded in the autonomous cars? Map providers, like maps, will provide the information of the obstacles about the static obstacles like buildings or the infrastructure along the road. But about the dynamic obstacles like objects, cars, pedestrians, and other such dynamic, like there are a lot of information in the environment that is now provided by the map. In that case, we have to go to the sensors, like you have to rely on the sensors provided in the autonomous vehicle. In that case, it is supercomputers embedded in like supercomputers embedded. As of now, there is, I don't think any supercomputer is there that is embedded in autonomous cars. And it is not possible in the market workers to embed the supercomputers. Only ECUs can be used in the if you going to the production cars, only ECUs can be used. But for developing the R&D purposes and all, we have used the computers that will be like our high-end computers, but normal computers only that we'll be using and integrating with the cars. And is there any open source simulation software to simulate connected workers, and which one is the standard protocol used in the connected worker? This is connected work for the connected worker applications. Simulators are it is I don't know. I don't know simulators are there. Whether yes, you can get the information of the other cars in the Carla simulator itself, but it is, I don't know. It is not possible to communicate one car to another as like in the V2X or connected computer like infrastructure is not. It is not. I don't know whether it is provided in such simulators. We can have the information of all other obstacles in the environment, and you can have the information about the infrastructures also. But communication between one worker to another worker, such feature is currently, I have to check whether it is there or not.
I think we can conclude. I think one more question, but I don't know whether you'll be able to answer or it is confidential. Is Tata Alexi using ROS for self-driving applications? Only if it's confidential, you don't have to say, is it ROS 1 or ROS 2?
Yes, we can tell it. Currently, we have used the ROS one for our self-driving cars for developing all the applications, and we have started exploring the usage of the ROS 2. Like some of the applications have migrated from ROS 1 to ROS 2, and we have tested it. But end-to-end testing and demos, everything is conducted on ROS 1.
Okay. The last question, can YOLO be used in ROS?
Can YOLO? Yeah, YOLO can be used in. It is a data set, like.
Okay. So thank you so much, Engineer Revathi, for your informative session and answering the questions patiently.